Welcome to the Explainer. So almost everyone has experienced it at some point, right? That sheer frustration of just struggling with math. For generations, when a student stares blankly at an algebra equation or, gets the wrong answer on a test, we've basically framed it as a failure of intellect. We assume they just didn't grasp the underlying concept. But what if we've been diagnosing the problem entirely wrong? What if the issue isn't actually in the student's head, but hiding in plain sight right there on the page? See, mathematics is not some abstract universe of perfect logic. It's actually an ancient user interface. And as it turns out, it's a user interface that's literally riddled with bugs.
Okay, let's dive into this because we are looking at a true cognitive whodunit here. Across completely different decades, different continents, totally different education systems, students don't just make random chaotic errors. Nope, they make the exact same, highly predictable and honestly sometimes bizarre math mistakes. Think about it. If math is purely logical, why on earth would a student in London and a student in Jakarta independently invent the exact same wrong answer? Well, this consistency is our first massive clue. It strongly suggests that there's a structural force out there, pushing their brains in a very specific, incorrect direction.
To put that into perspective, let's look at a recent Indonesian study of grade 7 students. An astonishing 66% of them, so 2/3 of the class, simplified the algebraic expression 4a plus 3b into 7ab. Now, the traditional knee-jerk reaction is to mark a big red X on the paper and declare that the student completely failed to understand the concept of algebraic variables. But researchers are actually telling us to step back and validate this. It's not a silly mistake, it's an intelligent error. The students are actually reasoning perfectly. The problem is, they're reasoning based on the visual clues they've been given, and those clues are secretly deceiving them.
So the crucial point is that we absolutely must separate conceptual errors from notational errors. A conceptual error means the student literally holds the wrong mental model of the math. But a notational error, that means the student actually applied perfectly correct, globally sound logic. They just applied it to a visually ambiguous input. Basically, they're confusing the notation with the concept itself, all because the notation isn't giving them the full picture. So they aren't failing the math, they're really just failing to read the invisible ink.
And this brings us to the real culprit. Researcher Scott Kim calls it the hidden state framework. If you look at the world of software design, hidden state is exactly what creates incredibly frustrating user experiences. You know the feeling. It's when you press a button and the system does something entirely unexpected just because it's secretly in a hidden mode that the screen isn't showing you. Kim argues that mathematical notation is essentially centuries-old unpatched computer software. Identical symbols produce totally different outputs depending on invisible modes. Experts have simply internalized these modes, but for novices, there's just no way to see them.
Let's look at the forensic evidence. It's time to decode some of these notational bugs.
Remember that 66% error rate we just talked about where 4a plus 3b magically became 7ab? Well, that happens because of the classic fruit salad approach to teaching algebra. Teachers desperately want to make abstract letters concrete for kids, right? So they say, okay, A stands for apples and B stands for bananas. But by doing this, they accidentally install a hidden mode. They're teaching students that letters are simply abbreviations for physical objects. So, when the student sees 4a plus 3b, they read it like a physicist reading 4 amps and 3 bytes, or, someone combining street signs. They just squish them together into 7ab. The student's logic is actually flawless based on the abbreviation convention they were given. The catch is that it fatally conflicts with the unstated mathematical convention where a represents an unknown numerical variable.
And this brilliantly illustrates a much wider issue, because we can actually see this hidden state problem mirrored perfectly in language. Just look at how spoken languages handle numbers. In Western languages like English, the spoken word 16 has unstated place values. The fact that the 1 means one group of 10 is a hidden multiplier. But over in East Asian languages like Chinese, Japanese, and Korean, the positional structure is totally transparent. 16 is literally spoken as 10, 6. 35 is 3, 10, 5. Because the notation is explicit rather than hidden, East Asian first graders massively outperform Western first graders in base 10 comprehension. The underlying math concept is exactly the same, literally only the transparency of the interface changed.
Now, if you want to see a truly absurd interface, look no further than fractions. This incredibly simple notation, just a number, a little horizontal bar, and another number, somehow forces students to juggle 5 entirely distinct mathematical meanings. I mean, are we talking about a part of a whole, like a slice of pizza? Is it a ratio of boys to girls, a quotient where we're actively dividing, an operator, or maybe a fixed position on a number line?
Absolutely none of these 5 meanings are indicated by the symbol itself. The student is just forced to guess the unstated context. Let's look at another classic hidden mode shift: parentheses. From the very beginning of algebra, students are rigorously trained to see parentheses as a rock-solid, incredibly clear signal for multiplication. So when you see a 3 nestled right up against a parentheses containing x plus 2, you know instantly you're supposed to multiply. That convention is just hammered into their heads. But then, out of nowhere, we introduce function notation. It visually looks utterly identical to multiplication, just a letter nestled right up against parentheses. But suddenly, bam, the invisible mode has changed. This doesn't mean multiply f by x plus 2 anymore. It means something categorically different. Apply the function f to the input x plus 2. Because the notation completely fails to signal this mode shift, a massive 43% of college algebra students in a 1998 study made predictable structural errors here. They tried to multiply because, well, the interface literally looked exactly like multiplication.
Now, what's really interesting about this slide is that this isn't just theory. A definitive 2004 study by Kirschner and Autry proved that students systematically over-apply mathematical rules simply because the equations look visually similar on the page. Students aren't unable to deal with the math, they are just responding to the visual salience of the notation. Because the true structure is completely invisible to them, they naturally just grab onto whatever visual patterns they can actually see.
Okay, moving on to making the hidden visible. How do we actually fix this without losing the power of expert math?
Think about written Hebrew for a second. Fluent Hebrew is written largely without vowels. The consonantal skeleton is there, but the reader actually has to supply the hidden state, the vowels, from their own internalized knowledge. But for learners, or children just starting out, there is this brilliant transparent scaffolding, a vowel pointing system that adds tiny dots and marks to explicitly show the missing vowels. Learners use this transparent notation until they fully internalize that hidden state. And then, once they have it down, they drop the scaffolding and read the compact, vowelless version fluently.
And this brings us to the parallel alternative principle. The solution to the math crisis isn't to invent some completely new foreign math language and throw away the standard notation. No way. Instead, we just temporarily expand standard notation to build the student's mental model. It's a simple 3-step process. Step 1. Start with an expanded, explicit, transparent notation where absolutely all the hidden rules are visible. Step 2. Allow the student to build a solid mental model of how the operators actually relate to each other. And finally, step 3. Once that's internalized, transition seamlessly right back into the conventional, compact notation.
This isn't just some pie-in-the-sky idea either. We actually have the technology to do this right now. Warren Robinette developed an interactive software environment that serves as a perfect example here. On a computer screen, students can grab a flat, compact string of algebraic symbols and physically pull it apart, fluidly morphing the equation into an explicit spatial tree structure. Suddenly, all those invisible operator hierarchies, like knowing multiplication comes before addition, expand out visually, right along with the hidden multipliers and the unstated order of operations. It literally turns a static, completely opaque line of text into a rich, structured hierarchy that the student can actually explore and understand. It's a real game changer.
So I want to leave you with the provocative thought that kind of completely reframes everything we've talked about today. Think back to the times you felt utterly lost in a math class, staring at a board full of symbols, feeling like your brain just wasn't wired for numbers. What if that wasn't true at all? What if your logic was actually perfectly sound and you were simply the victim of an interface design that hid the most important rules from you? What if you were never bad at math, but just trying to read a fundamentally bad interface? Thanks for exploring this fascinating hidden world with me on this explainer. I really hope you walk away seeing the numbers on the page in a whole new light.